Welcome back. So we motivated the goal of performing SGD without the gradient information. So let's see how we can do this. Okay. So let's first build some intuition. Okay. And to do that, let's focus on a scalar function. So let's recall the definition of a derivative. Okay. So what's the derivative? It's basically some limits, right? So as I'm writing here, and if the function is noise such that the left derivative and the right derivative are the same, we can basically write down the formula for derivatives using either one of these formulas. Okay. So this is a limit. So we basically, if we want to calculate the derivative at one point, we perform some slight perturbation and see what's the change in the function value. And then we divide that by that perturbation such that when this perturbation goes to 0, we can find the slope of the line tangent to W. And that's basically nothing but the derivative. Okay. Now, let's imagine that instead of setting mu to go to 0, we use a mu which is not 0 and fixed, but is very, very small. And let's consider this quantity. Okay. So it's f evaluated at W plus mu minus f evaluated at W minus mu divided by 2 mu. Again, if mu goes to 0, this is nothing but the derivative of the function. But if mu is not going to 0 and it's small, we still expect this to be a good approximation of the derivative. Okay? So for a small mu's, this should be a good approximation. Okay? Now let's look at this. So all we need is two function evaluations. We don't need any gradient, or in this case, derivative calculation. And this is basically what we wanted, right? So if I were to minimize, let's say, this function f, instead of using the derivative of f and performing gradient descent, I could have used this approximation, which doesn't require the gradient, only two function evaluations to perform my gradient descent, basically. Okay. Now the catch is that I think it is intuitive to expect to incur some bias depending on mu, right? So the smaller the mu, the better the approximation. Therefore, the smaller this bias. And surely, as mu goes to 0, the bias vanishes, and our approximation converges to the true derivative of the function. Okay. All right. So that's hopefully that gives you an idea of what we want to do. Essentially, we want to just use function evaluations and form an estimator that looks very similar to what we discussed in the previous slide. But the catch is the models have billions of parameters, right? So they're not. So that means that our loss functions are not scalar functions, right? So the domain is multidimensional. So we want to extend this idea to multiple dimensions. Okay, and to do that, it's what we do. We're going to resort to the power of randomness, basically. So we're going to view the estimator. We are still in one dimension. We're talking about the scalar functions, but we're going to view the approximation that we talked about in the previous slide as an expectation now. The expectation over random directions in R. So that means that the directions are only left and right. Okay. So mathematically, this is what I'm talking about. Let U be a random direction. So it's either right or left, 1 or -1. I'm using a language here which is going to become apparent why I'm doing that. So let U, this random direction, be a vector in R lying on the surface of the unit sphere. So what's the unit sphere in R? It's nothing. The unit sphere is basically the interval between -1 and 1. And the surface of the unit sphere in R is nothing but -1 and 1. Okay. Now consider this random variable. Okay. So it's very similar to what we had in the previous slide, except I'm introducing U here and U here. Okay. And I'm also slightly changing the expression we had in the numerator. Okay, this is a random variable because u is random. U is a random direction. G is a function of u. Therefore, G is also a random variable. Okay, so let's talk about the expected value of this random variable. So when I take the expectation with respect to u, so the selection is uniformly at random, so it's equally likely to go left or right. So therefore, the expectation is actually very simple. It's half times this quantity, when this corresponds to the case where u is equal to 1, times this other quantity. So you have to get rid of this. And this corresponds to the case where u is equal to -1. Okay? If you do the simplification, which is quite easy to do, you'll see that the expectation is nothing but the approximation we talked about in the previous slide. Okay? So therefore, the approximation is nothing but the expected value of this random variable. Okay? And obviously, as we said before, when mu is small, this is going to be a good approximation of the true derivative of the function. Okay? So what's the conclusion then? This new random variable I defined is an unbiased estimator of this approximation, which is an approximation of the true derivative of my function. Okay? Now, let's see how we can build upon this idea to go to multiple dimensions. This is what it said. So we select a random direction on the surface of the unit sphere. Now, if we are in multiple dimension, we are still going to do the same thing. Okay? We are still going to sample u uniformly from the surface of the unit sphere, but now our unit sphere is in RT. Okay? So in particular, if d is equal to 2, this is how the unit sphere look like. So I'm going to sample a vector on the surface of this circle, basically. Okay. Now our estimator is going to be exactly the same as what we talked about in the previous slide. It's going to have this form. In particular, it has, let's say, a random. So this is the random magnitude, if you will, and this is the random direction. So therefore, it's a random estimator. Okay. So this is what we're going to use to optimize loss functions without the gradient information. Okay. And this estimator is called zero-order estimator because it only uses zero-order information, basically the function values. It doesn't use first-order information or the gradient, nor the second-order information, the Hessian. Okay. Now, one detail here is that instead of using the unit sphere, you can also use other distributions. For instance, you can use Gaussian distribution to sample u. Okay, so and the reason is that there is actually a very neat connection between vectors that are distributed according to a normal distribution and vectors that lie on the unit of the sphere. In particular, if u is a Gaussian vector, its normalized version lies on the surface of the unit sphere. All right, so how can we use it for optimization? So imagine that we are minimizing a stochastic loss, such as this. Again, we think of this as minimizing the average loss over the training data. We initialize our iterative algorithm. We use some learning rate, and we're going to fix the smoothing rate mu. And we're going to see in a minute why I call this the smoothing rate or the smoothing parameter. Okay. So we have an iterative algorithm. For capital T number of iterations, we're going to sample a random direction u from either the surface of the unit sphere, or according to the Gaussian distribution. this part is identical to SGD. We sample a mini batch, and then we form our update vector. Okay, so the update vector is basically it has a mini batch form, so it's the average of the zero order estimator we discussed in the previous slide, and then we're going to use it to update our parameter by using this simple first order update that we have seen more than a few times in the course so far. So this is called the zero order SGD method, right? So it is almost identical to SGD, except that instead of using a stochastic gradient, we use the zero order estimation of the stochastic gradient to update our parameter. And the zero order estimation as an estimator, as I mentioned, only requires access to function values, not the gradient. So it can be used to, for instance, solve those three motivating examples that I mentioned, right? So you can use versions of this in online RL, you can use versions of this for adversarial training, and also recent results have explored utilizing this idea when fine-tuning large language models. Okay, so one point I want to make here is that given that there are a lot of random operations here, so the direction is random, the samples we are using are random, this approach is going to suffer from a high variance. So again, we are using a random estimator. So this random estimator is going to have some bias, also potentially large variance. So it's something to try to deal with. So in the most simple case that we saw before, in order to deal with the high variance, was the idea of mini batching, where instead of one sample, we used, let's say, B samples. Okay, so we can use the same idea here. So to lower the variance, instead of using one random direction, you can use a mini batch of random directions. Okay, so in particular, you can form this estimator, which is basically the average of average over k random directions, right? And these random directions are either chosen from the unit sphere or according to a Gaussian distribution. So now let's talk about that smoothing term I mentioned. Why I refer to mu as the smoothing parameter. Okay. So recall, this is the estimator we talked about. So we started with this estimator. This is the approximation of the true gradient, which is a random variable because the direction is random. We show that its expected value is going to be something like this. So G mu, and this was the approximation of the true gradient. Now, one question is that if nabla f is the gradient of f, and I'm keep referring to this G mu as approximation of the gradient, is this itself the gradient of any function? And if so, which function? Okay, it turns out that the answer is yes. G mu is actually a gradient. It's a gradient of some function. Which function? Is f mu, which has this form. So it's as if you're taking f and you're shifting the parameter in a random direction with a tiny amount mu, and then you're taking the expectation with respect to your random choice of direction. Okay. Now this f mu is called the smooth version of f. Okay. Such that when the direction is chosen, let's say according to the Gaussian distribution, the technique is called Gaussian smoothing. Okay, so why do we call it a smoothing? Because it turns out that this function f mu has sensitivity parameters or properties that are nicer than the original function. So what does that mean in terms of the terminologies we've discussed before? So for instance, assume that the original function is Lipschitz and smooth. it turns out that the f mu is going to have lower Lipschitz parameter and also lower smoothness parameter. Even more, if the original function f is not smooth, it turns out that f mu can be smooth. Okay, and in fact, the smoothness parameter typically is proportional to the inverse of the smoothing parameter mu. So that gives you an idea of why we call mu the smoothing parameter. Okay, because it controls how smooth and nice f mu is. Okay, in particular, mu controls the smoothness and approximation trade-off. Okay, so the larger mu is, the nicer this function f mu is going to be, because it's going to have better smoothness parameter, for instance, but the approximation is going to be worse. So the distance between f mu and mu is actually going to be larger. On the other hand, when mu is small and in the extreme case approaches 0, then f mu is going to approach the original function. And as a result, the sensitivity parameters are going to increase. That's why we call mu the smoothing rate or the smoothing parameter. All right. So, but why this operation helps to smooth the function? Okay. So recall, this is the gradient we talked about. So g mu, or approximation of the gradient, is the gradient of another function, and this function is nothing but the smooth version of the original loss f. Okay. So the intuition here is that the expectation is essentially an integral. Okay, and integrals tend to make functions smoother and nicer. Okay. So, because if I give you a function, the derivative may not exist, right? But many times the integral, especially for instance for a scalar function, the integral does exist, right? And tends to be nicer than the original function. Okay. Indeed, f mu, this is a smooth function, is nothing but the convolution of f and the PDF of u. Okay, so what's the convolution? So recall the convolution between two functions is given by this expression. Okay, so basically what we are doing, we are taking the original function, which may not be as nice and as smooth as we are hoping. We convolve that with the PDF of this random direction u, for instance, the PDF of a Gaussian distribution, and then we're going to focus on the resultant function, which we call the smooth version of the original function. Okay. Now, here we are talking about this idea in the context of optimizing a function without accessing the gradient, but it turns out that this idea is very, very powerful, and you can use it in different areas as well. For instance, when you are analyzing deep brain models with non-smooth activations, for instance, ReLU. Okay. So here I'm showing the plot of the ReLU activation. So as we talked about, ReLU of x is basically the max of 0 and x, and it is non-smooth because at 0 here the derivative doesn't exist. But if you take it and let's say convolve it with the PDF of Gaussian, you're going to get something like this, which is also referred to as the soft plus ReLU activation. Okay. So what that means is that if you have some results for deep brain models with the smooth activations, okay, you can extend that to deep learning models with non-smooth activations, such as the ReLU activation, which we typically use in many practical settings. Okay. All right. So, but let's go back to the implication for optimization, right? So, we talked about the zero-order SGD method, right? And we said that basically the estimators we are forming can be thought of as an unbiased estimator of g mu, which itself is the gradient for another function, the smooth version of the original loss function f. Okay? So therefore, our zero-order SGD method is essentially a SGD, but for a different problem. Okay? So instead of minimizing the function f directly, which requires access to the true gradient of the function, what we are doing, we are minimizing the smooth version of the function using SGD. And this process turns out that it doesn't require access to the true gradient of the original loss function. Okay? Now we have two problems, therefore, and these two problems are different, and they're going to become more and more similar as the smoothing parameter approaches zero, because f mu, the loss function for this new problem, is going to converge to the loss function of the original problem. Okay? Now this idea actually can be leveraged quite easily to prove a theorem that I'm stating here. Okay? So what you can show is that if the smoothing parameter is small enough, for instance, it scales with 1 over d, the dimension, times the square root of t, and if the step size is small enough as well, the zero-order SGD method is gonna satisfy this nice bond. Essentially, the accumulation or the average of the gradient norms is going to be bonded. So the bond depends here on multiple parameters. I'm focusing on two important parameters here. The first one is the total number of iterations. So the bond shows that similar to SGD, we have two terms, a higher order term, the first term, and a dominant term, the second term. Okay? And as t, the total number of iterations, goes to infinity, the bond becomes smaller, meaning that the method converges to a stationary solution of the original minimization problem. The second problem, parameter that I'm focusing here, is the dimension. Okay? So here we see a dimension dependent result. Okay, so for the first time, the dimension explicitly appears in the bond, and in fact, the larger the dimension, we can see that the larger the bond. Okay, so it turns out that in many scenarios, the dimension, the dependence on the dimension is unavoidable, and in fact, there are many settings where the zero-order SGD method is the optimal algorithm that you can use in the worst case. All right, so there you go. This is another important modification to SGD that helps us to broaden the applicability of SGD to not only scenarios where we have access to the gradient, but also scenarios where we don't have access to the gradient. And along the way, we hopefully learn some useful mathematical concepts that actually transcend beyond the context of this lecture. So for instance, as I mentioned, this is a very useful tool to analyze deep learning, properties of deep learning models that utilize non-smooth activation functions. That's basically the end of our first module. We're going to switch gear slightly and talk about some basics of deep learning architectures and basic deep learning training strategies in our second module. I'll see you there.